This is How to Math with Dr. Ian Lundholm. In today's episode, vectors and lines. Now I'm going to level with you. This material is not going to be very hard for many of you. You've been through Calculus 3. But if you have not been part of that environment yet, we're going to do some basic stuff with vectors and lines today. Some of it will be review from the parametric vector form stuff that we've done already, solving linear systems of equations. And here we go. Vectors are different than scalars. Scalar quantity is just like a number, like you're used to working with. And a vector quantity has both direction and magnitude. We've been working with vectors already in this class, so let's not spend too much time there. Here's a vector in R2 and another vector in R3. Here's some notation about translating between points and vectors. Here you can see in the middle we've got an arrow over top of 0p. In this context, 0 is the zero vector, and so what that notation is highlighting is the fact that we're going from the origin to the point P and creating a vector between those 2 points. As you will see, oftentimes, I've gotten used to it from using GeoGebra. I use like a big letter for a point and a small letter for a vector. So we'll keep going here. Yeah. So here's an instance where they're rewriting that vector from 0 to p as just a small p, like I normally would. I don't normally bother with writing the arrow over top. Okay, this is all really basic stuff. All right, here is our first theorem of the day. We've got two vectors, v and w. V equals w if and only if their entire, all of their components are equal. This is how you find the magnitude of a three-dimensional vector, which the magnitude of a vector is just its length. That x squared plus y squared plus z squared is just the Pythagorean theorem on a three-dimensional vector. It is true that the zero vector has a length of 0, and that is the only vector that has a length of 0, or a magnitude of 0. And for any scalar number, you can multiply a number times the magnitude of a vector, and it works out that way. Not too surprising. You're just taking a scalar multiple of the vector that you have. All right, and there's the Pythagorean theorem in 2 dimensions. Good grief, let's keep it moving. We could find the magnitude of all of these vectors. I think the thing to point out is that, we've got a negative 2q here, and to find the magnitude of negative 2q, all you have to do is multiply the magnitude of q by 2, because it's twice as long and just in the opposite direction. So length we always measure using positive numbers. All right, here's a vector that's not necessarily starting from the origin. Sometimes we have to do that when we're connecting lines in space and stuff like that. Sometimes we have to make vectors that don't necessarily start at the origin. I'm gonna keep going. Even though those vectors are in different places, technically they're the same vector because they have the same length and magnitude. These two vectors are also the same length and magnitude. It just so happens that 0p is in standard position. All right, this is just more of the same notation, blah de blah. All right, vector equality, same length and direction. Zero vector, zero length, no direction. Scalar multiplication, addition. This is, vector addition. You can make a parallelogram out of the two vectors that you're adding. Man, you've seen this before. Here we go. Again, we've got scalar multiplication, addition. It's all good. Tail to tip method. All right, here's an interesting thing that we get to do. We get to show that the diagonals of any parallelogram bisect each other. Welcome to high school geometry class. We're going to give points to each of the vertices on this parallelogram, A, B, C, D, and we're going to create a midpoint in there. Right now, the midpoint's a little bit off center, it looks like, but we are going to show that that midpoint is, in fact, at the intersection of those lines, AC and BD. So what we're going to do is construct a midpoint right from the get-go. Construct a midpoint along the vector AC. And if we have that midpoint between A and C, we're halfway there. If we can show that M is also the midpoint of BD, then we're going to be great. And I have a colored version of this. Oh my goodness. Where did my annotations go? Oh, that's so sad. All right, let's see. We'll do this in real time. Come on. All right, BM right here. Going from the point B to M, I'm going to cheat a little bit and go towards the center so it looks nice. BA, starting at B, going to A. AM, starting at A, going to M. All right, so we see that BA plus AM is the same thing as BM. And then CD plus MC. So we've got CD plus MC is the same thing as, well, MC plus CD. That's really the same two vectors, just in a different order. Okay, and then I need a different color for MD. And so you can see by these, I don't know, sums of vectors that we've done, BM and MD, same direction, same length. That means that we have successfully bisected BD using the point M. And therefore, the diagonals of a parallelogram bisect each other. That was fun. Vector subtraction is very similar to addition. Instead of the long, the long diagonal in this diagram, where if we were going to connect this one to this one, this would be U plus V, that vector. U minus V goes along the other diagonal, and starts from the tip of V and goes to the tip of U. But, that vector U minus V has magnitude and direction the way that you normally would think about it. Yeah, we're going to keep going. I don't want to get stuck. Here we go. That's what it looks like to subtract two vectors numerically. Vector subtraction is really handy for finding the difference between 2 points, the distance between 2 points. Literally, all you do is find the magnitude of the vector that starts at one point and ends at the other point. So yeah, finding the distance. I mean, you've all seen the distance formula before. We're gonna keep going. Yay! That's what it looks like in a proof. Here we have 2 points, P and Q. That's what it looks like to connect P and Q with a vector using subtraction. And we're able to see that the distance between P and Q is the square root of 17. A unit vector is a vector of length 1. I'm sorry, guys, if this is horrible. It is Friday afternoon, and I am really hoping to get this done so that it can be prepared for you guys on Monday. And this is, this chapter, I'm trying to go through it fast because it's really not that exciting. There is one interesting problem that we'll get to later. All right. I guess this one shows you that if you start off with a vector v and it's not a unit vector, you can make it into a unit vector by dividing by its magnitude. So you can create a unit vector u by multiplying, or by dividing this vector v by the square root of 14, and then the magnitude of u is 1, the way that we want it. All right. Here, if we'd like to find a midpoint between 2 points, P1 and P2, first we could create the vector that goes from P1 to P2, and then once we've done that, here, let's see. I'm going to draw. Sorry. P1, P2. All right, so here's the plan. We find a vector going from P1 to P2. We'll call that vector, I don't know, V. That might be something different on this slide once I click it. But then what we're going to be able to do is do P1 plus V. Well, actually, not all of V, 1/2 of V, and P1 plus 1/2 of V will take us to the point where we want to be. So, really hiding in the background, there are two vectors here going back to the origin. And if we add P1 to 1/2 V, we should be at the midpoint where we want to be. All right, let's see what happens here. Going on to the next slide. Boom. All right. That's a nice little visual. Boom, 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 boom. And here's what the math looks like. There's our vector V that I came up with on the last slide. And we're taking 1/2 of V there. Add them together. And you get the midpoint, which is cool. Midpoint right here. Okay, great. Oh, now we're getting daring, and we're going to find 2 points that trisect the segment between 235 and 8, -6, 2. In order to do that, same overall setup as before. We're going to find the vector that connects P and Q, and then we're going to use 1/3 of that vector and 2/3 of that vector to come up with A and B. All right, so there's all the math. Cool. All right, now we're looking at a quadrilateral, ABCD. Show that the midpoints of the 4 sides are the vertices of a parallelogram. All right, so we're constructing 4 midpoints along the outside edges. And if we can prove that the vector from M1 to M2 is the same as the vector from M4 to M3, then we'll have shown that these two vectors, that these two sides of the parallelogram are actually parallel, and we'll be in business. Whoa. Okay, well that was kind of a letdown. That part isn't on there. Suffices to prove that those two things are parallel. I'll leave that as an exercise for you, or maybe we can talk about that in Pronto, because I don't want to make this video too long. All right, so yes, they are parallel if and only if they're in the same direction or opposite directions. That makes sense. So that they are scalar multiples of one another if they are parallel. All right, we're good. Cool. All right, and the equations of lines here should seem very familiar. We've seen this before using parametric vector form. Here, the vector d is our direction vector, and the point p0 is our starting point. And so you're going to see this happening very soon. Yeah, that looks familiar, right? To create a line in 3 dimensions, we need a point and then another vector that has a slider attached to it so that t can change and we trace out the line in 3D space. And here are the corresponding parametric equations of a line. So that's all very familiar. All right, let's find an equation for the line through those 2 points. In order to create that line, we need one of the points on the line and we need a vector that goes through both points. And to find that vector that goes through both points, you guessed it, we subtract. So we subtract the 2 points to get the direction vector d. And then we use that as kind of the slope for our line and attach that to the parameter t, and we're good to go. That traces out a line in 3 dimensions. All right, for finding the equation of a line through that point in parallel, we just borrow the same direction vector and make sure that it goes to the point Q. I would be happy to talk with you about this more in Pronto if you still have questions. Oh, sorry. We have 2 lines, L1 and L2, and we would like to find the point of intersection between those 2 lines if they happen to cross. And that would actually be a very special thing, right? 2 lines in 3D space actually intersecting. These should be pretty special lines if they do that. Essentially though, what we're gonna do is set the x values equal to one another, set the y values equal to one another, set the z values equal to one another, and solve the system of equations in 3 equations and 2 variables and see if we get something that's consistent. We do some row reduction and find out, hey, those 2 do intersect when s is -1 and t is -1. And so we can find that point of intersection by just plugging s and t into our original parametric equations, and we're good. Cool. This might be the last example of the day, or of this section at least. Find equations for the line through P that meet the line L at points 3 units away from the initial point P0, 1, 2, 0. So we've got this line, and let me get you a little bit of a diagram here. We've got this line that goes to the point P0. What we're trying to do is create 2 new lines through 2 new points. Q1 and Q2 are the 2 new points that are 3 units away from P0. And we want to come up with equations for the pink line L1 that I have here and the blue line L2 that I have here. In order to do that, we're going to need a point on that line and the direction vector that's, connects, say, for line 1, we're going to need to get the direction vector from Q1 to P. For line 2, we're going to need to get the direction vector from Q2 to P. But first, we need to figure out what Q1 and Q2 are. How can we travel 3 units down this line from P0 to actually create Q1 and Q2? So here we go. We're going to take a look at the direction vector that was in that last, our original line L. And we'd like to know the length of this direction vector so that we can make sure that there are 3 units. We use this direction vector to create another point 3 units away from P0. And very thankfully, the direction vector V actually has magnitude 3. And so literally all we have to do is we just add our point, P0 to D, and then we take our point P0 and subtract D from it to get Q2. And it's really just as simple as that to get those. It would have been a little bit tougher had the direction vector not already been of length 3. We would have had to scale the direction vector appropriately in order to get the right distance, but this time it just worked out so that we only needed to multiply it by 1. And so now we have points Q1 and Q2, and in order to come up with the equations for the lines, all we do is, subtract Q1 and P, and then we subtract Q2 and P, and those would give us the two direction vectors that we seek to actually create the line L1 and the line L2. Cool. Good grief. All right, and there's one more thing that I'd like you to do before our next video lecture. There is a video on 3 blue 1 brown that I'd like you to check out called Dot Products and Duality. That will set us up nicely for our next lesson because we're going to be talking about dot products. So hopefully I will have a card up here in YouTube that you can click on and watch that at your leisure. This has been How to Math with Dr. Lundholm. Remember, you have online homework to do, and now you're ready for it. I'll see you in the next one.